Hello friends, let's begin the lecture number 14 of Advanced Thermodynamics. So in the previous class we actually started with discussions on what we call the equations of state, which are the equations that connect the generalized force, generalized coordinate and temperature of any object in a mode of interaction. And for simple systems, that is systems with only a single mode of interaction that is possible, we have one generalized force, one generalized coordinate, and therefore the relationship between the generalized force, generalized coordinate and temperature in such a system is termed as the equation of state for that system. And if we have multiple such interactions that are possible, the combinations of generalized force, generalized coordinate and temperature, the relationship between them for each of those would actually constitute the equation of state corresponding to each of those interactions for that system. So when we discussed the simple compressible systems, we said that since the generalized force is minus P and the generalized coordinate is V, we said that the relationship between P, V and T constitutes the equation of state. We also looked at simple calculus to start from the fundamental equation of thermodynamics, which says du is equal to Tds minus Pdv. And using that, we were able to write a set of three equations. One for actually defining the T and V, Tds and Pdv. So T and P in terms of the variables S and V, and then by equating the second derivatives in opposite orders, we were able to write a cross derivative expressions of T, P and S and V. So we were able to get three equations from this equations. We called it 1, 2 and 3. Similarly, we could get three equations from the definitions of enthalpy, Gibbs function, Helmholtz function and Gibbs function, and the third equation in each case where the cross derivatives were equated are called the Maxwell's relations, which relate the derivatives which contain only measurable quantities on one side to derivatives that contain the entropy on the other side, and therefore it would be a tool, or these equations would help in determining the entropy or the derivative of entropy with respect to V or P, or the derivative of V or P with respect to the entropy in terms of P and T measurements. So that is the way we got the expressions, and we said that these equations are useful in expressing the unknown or the unmeasurable variables such as internal energy, enthalpy, entropy in terms of the measurable quantities such as pressure, volume and temperature. So that goes to basically indicate that the equations of state can be not necessarily simple equations, but can also be complex equations. It could be algebraic equations, it could be equations that involve partial derivatives of some variables with respect to the other. So what would be necessary in constructing any property tables would be extensive measurements of P, V and T, and then trying to fit either a regression or a equation to the set of equations, the set of data that we have got, and from that we should be able to differentiate and get expressions. We also have equations of state which are not entirely based on measurements. Say for example, the tables of water, steam or refrigerant, etc. are based on extensive measurements that were made on these fluids. But there are equations of state which have a much simpler form than that. The simplest of those is the ideal gas equation of state, which basically comes from the Boyle's law and the Charles law, which are more than 150 years old now. So the relationship that PV by T is a constant for a substance which is behaving, so a substance which has PV by T as a constant is said to behave like an ideal gas, and it follows the assumptions that are used in the kinetic theory of gases, right? So what are the assumptions in kinetic theory of gases? We assume that the vessel is much larger than the average space between molecules in the thing, and the average space between molecules is much larger as compared to the size of the molecules themselves. So the molecules are moving in random motion in the space, and then each molecule is moving as if it did not know that the other molecule existed. There are collisions which are perfectly elastic, and so on and so forth. So there are several assumptions that come, and based on that we define the various properties such as temperature, which is proportional to the average kinetic energy of molecules, and the interaction between molecules is neglected in the case of ideal gas. So with this we get an equation of state which is very simple in form, and that constitutes the simplest possible equation of state that has ever existed. So we'll start with the simplest of those. We'll start with the ideal gas equation of state, and then after understanding how to calculate the property relationships, or how to calculate the internal energy, enthalpy and entropy changes for ideal gases from the values of pressure, volume, temperature that are related using the ideal gas equation of state, then we can move to more complex equations of state. Okay. But what we will again recall is that an equation of state is not entirely representative of a particular substance. It is representative of a certain range of pressures and temperatures for a substance. For example, we know that when we say oxygen or nitrogen, we can think that yes, they are gases. But are they gases? Yes, they are gases at atmospheric temperature and pressure. But if I am able to bring the temperatures down below, let's say, minus 170, minus 180 degrees Celsius, we are able to liquefy nitrogen and oxygen, and we are able to actually fractionate nitrogen and oxygen and separate nitrogen out, because nitrogen boils at a higher temperature than oxygen, although the difference is very small. So given the right conditions, it might become a liquid, and take the temperatures even lower, it might become a solid. So there are temperatures at which there is a solid liquid equilibrium, where solid melts and becomes liquid, and there are temperatures at which liquid melts, liquid evaporates and becomes vapor, and so you have the entire range of phenomena. And when you come to atmospheric conditions which are much higher than these temperatures, you will find that these gases behave like ideal gas. So it may be fascinating to even imagine, for example, a substance like iron, which we know is solid, given the right conditions of temperature and pressure, can be an ideal gas, isn't it? So what we need to imagine, or what we need to understand, is that the equations of state are representative of a particular substance in a particular range of pressures and temperatures, and given the right range of pressures and temperatures, you would get the various phases and various states of the same substance, and therefore the equations of state can be different. And you can also imagine that if I am able to normalize these equations with respect to some critical or some characteristic parameters, then maybe more than one substance that exists in nature could have the same set of properties which are non-dimensionalized with respect to these characteristics. That would again constitute what we call as generalized charts, which also we will be talking about. So in that order of complexity, increasing order of complexity, we will be looking at ideal gases first, then we will look at deviations from the ideal gas equation of state and try to understand the concepts such as compressibility, concepts such as generalized compressibility chart, and also the different forms of real gas equations of state. And then the familiar property tables that we know of, steam tables and refrigerant tables. So we'll put them all into perspective. We'll understand how to treat solid liquid phases, how to treat gas phase, how to treat the phase change areas, and so on. Right? So we'll look at all of these so that we get a complete picture for simple compressible systems of what kinds of equations of state or what kinds of property relations can actually exist. Right? So this is basically what we will be doing. To start with, we'll understand the ideal gas equation of state. So for that, let's move on to the whiteboard. Okay. So here we are. So we'll be talking about the ideal gas equation of state. Oops. Okay, I'm just trying to use a new gadget, and that's why I'm getting into some kind of difficulties. Okay. So what is ideal gas equation of state? These actually are derived, as I told you, from the Boyle's law and Charles law. So it comes from PV over T is a constant, and or this can be written in the form of PV is equal to N into R into T, where this R is the universal gas constant, and has a value equal to 8.314 joules per mole Kelvin. This can also be written as kilojoules per kilomole Kelvin. Okay, so this is the value of the universal gas constant, and all gases that behave like an ideal gas have this relationship. So the constant is the same. This P is the pressure, and V is the volume that it occupies, N is the number of moles that occupy that volume, and T is the absolute temperature. So this is your ideal gas equation of state. There are multiple ways of writing this equation of state. So let us look at that. So now if I write this N, which is the number of moles, to be the mass of the gas divided by its molecular weight, okay, then I'll be able to substitute into this. I'll get an MRT here divided by capital M. So if I write the universal gas constant divided by the molecular weight as the gas constant R of this substance. So this gas constant R has a unit of joules per kg Kelvin. Okay, it's joules per kg Kelvin. It can also be written in the form of kilojoule per kg Kelvin, depending on what the values that you want, or depending on how large or how small the numbers actually become. In some calculations we use the kilojoules, in some calculations we use the joule. So this R then is the gas constant of that specific gas, because we are dividing by the molecular weight of that specific gas. So this gas constant is universal, which is basically the same value for all species that behave like ideal gas, all elements that behave, or all substances that behave as ideal gas, whereas this R is actually a mass-based gas constant, which is specific to one substance. So if I substitute this expression and this expression into this equation, then I get PV is equal to M into R by M into T. So this becomes the small r. I'm sorry about my writing today, because I'm just trying to use a different device. Earlier I was writing on my touch screen directly with my hand, and that had one kind of control, and now I'm trying to use a tablet device, and so I'm having a slightly different feel. So this is M into R into T, where this R is the gas constant, mass-based gas constant. So this expression is what we call as the equation of state in terms of mass. And now taking this M to this side, I'll get V by M. I can write volume per unit mass is the specific volume small v, and therefore I can write this equation as PV is equal to RT. So this is the most common form of the equation of state for ideal gases that we would be using. In this case, this P is the pressure, which will be in pascals or kilopascals or bar. In SI units it is pascals. This would be in meter cube per kg. and this would be the absolute temperature in Kelvin, and this therefore would go to joules per kg Kelvin, because the product of Pascal into meter cube, this is newtons per meter square, meter cube is Newton meter, which is joules. So this is joules, and this R is joules per kg Kelvin, and this is Kelvin. This is meter cube per kg, and therefore you get here you get Newton meter per kg, right? And so that is joules per kg. So this will be joules per kg Kelvin into Kelvin. This is joules per kg. So that's the equation consistent in units. So this PV is equal to RT is the form of equation of state that we would be commonly using. Okay. So then the next thing that we will be writing is the expression for work, which we can write in terms of W on is integral minus P dV, particularly for reversible processes, because for any process it is P external dV. For a reversible process it is P dV from the initial state I to the final state F. Okay, so this is the expression that we would have. In this case, if I'll be able to express this P in terms of V using the equation of state, which is here, then I'll be able to write P is equal to RT by V, and this V is M into small v. So if I take out the M, then I get this is minus M, and this RT is also constant. So RT integral from I to F of dV divided by V. Okay, so this is basically what you get. So this integration basically then will become, this I is VI and this F is VF. So you get this will become this integral can be replaced as minus MRT log. Okay, there is no space to write there. Okay, so I'll write it here then. The work on becomes equal to minus MRT log VF divided by VI. Okay, so this is the expression that we get. So this is a simple integration that we get. And this we can do for an isothermal process because T is a constant, so it can be taken out of the integral. But if it is not an isothermal process, then this T cannot come out of the integral and it will stay inside the integral. And so this is for a reversible then isothermal. Okay, for a reversible isothermal process, when T is a constant, I can write the work done on is minus MRT, and this is equal to minus W by, this is the negative of work by, so the minus term will get cancelled, so by W by would be equal to MRT into log of VF by VI for a reversible isothermal process. Okay, so this is the way we actually end up looking at various things. So now the relationship between PV and T is reasonably well understood. So if I know PV, I can calculate T. If I know PT, I can calculate P, and so on. So that is something which this can be done. Now let us look at the other variables, the internal energy U, the enthalpy H, and the other quantities of course is G minus Ts and U minus Ts, so we'll not bother too much about them. This U is nothing but the capital U per unit mass that we looked at earlier, and this H is capital H per unit mass. And in ideal gases, because we are actually dealing with gases that the molecules are so far apart from each other, the pressure which basically is going to bring the molecules together, so long as the ideal gas behavior is respected, these molecules never come close enough together to be able to influence each other, and therefore the energy stored in the object is not going to be affected by pressure. Only when the molecules start interacting with each other, the effect of pressure is important, and therefore U is a function only of temperature. This is the first understanding that we have about ideal gases. So when the gas is ideal, so this is only for ideal gases. Okay, for ideal gases we can say U is only equal a function of temperature. Sorry. Similarly, now H, which is U plus PV, and in this case U plus PV is U plus MRT, because PV is equal to MRT. Okay, so this is M. So this is also only a function of temperature, because this R is a constant and M is a mass. So if I divide throughout by mass, I get here U is U of T, and here I get H is equal to U plus RT. Okay, and in the simplest case, where I can say we have defined these quantities called Cp, which is del H by del T at constant P, and Cv, which is del U by del T at constant V. Now, since P and V are not going to affect these things, and this is only a function of temperature, this actually becomes dH by dt. So it is not a partial derivative, but it is a total derivative, because H is function only of temperature, and this will be du by dt. Okay, so we can actually write this expression as H is equal to dH is equal to Cp dt. Okay, and similarly here you can write du is equal to Cv dt, where since H and U are functions only of temperature, the Cp and Cv are also functions only of temperature. Okay, so then if I write this expression, if I differentiate this expression, I get dH is equal to du plus R, because this T, when I differentiate, sorry, this is R dt rather. Okay, so if I substitute from these two into this expression, I get Cp dt is equal to Cv dt plus R dt. So if I cancel out the dt throughout, I get Cp minus Cv is equal to R, the gas constant. So this is one relationship. The difference between the specific heat at constant volume and specific heat at constant pressure is equal to the gas constant of the particular gas, okay, which is given as R. So this is one relationship. The next one is that we always know that we write this ratio of Cp by Cv as gamma. Okay, so this is the other one. So if I write the Cp minus Cv is equal to R in terms of this, then I get Cp minus Cv is equal to R. If I divide this throughout by Cp, I get 1 minus Cv by Cp, which is 1 by gamma, is equal to R by Cp. So this is one expression that I will be using. And if I divide this throughout by Cv, then I get Cp by Cv, which is gamma, and minus 1 is equal to R by Cv. This is the second expression. So now these two expressions can be useful in deriving the expressions for the other quantities. So du and dH can then directly be evaluated using the specific heats that we have defined now, and they are only functions of temperature, and so if the specific heats are known, then we should be able to define all the other quantities in terms of those. Okay, so that is the way ideal gas properties are evaluated. Now ds, the change in entropy, internal energy and enthalpy are done. So for entropy, we use this expression Tds is du plus Pdv. This is the equation for this is the what do you call fundamental equation of thermodynamics divided by mass, because we are used to writing this capital S, this capital U, and this capital V. Now if I divide throughout by mass, then I get specific entropy small s, specific internal energy small u, and Pdv. So this is the expression that I get. So I'll be able to write ds is equal to du can be written as Cv dt by T. Okay, so they're bringing this temperature here, plus P by T dV, and using PV is equal to RT, which is the ideal gas equation of state, I'll be able to write P by T is nothing but R by V. So this will be equal to Cp dt by T plus R dV by T. Okay, so this can also be written as Cp d of log T plus R d of log V. Okay, so then this is the expression. So if I integrate this, I get Sf minus Si for any process I to F is basically the integral of these two. So it will be integral of Cp of T into d log T, or it will be Cp of T divided by T dt plus this. So this is from Ti to Tf. Similarly, this will be integral from Vi to Vf of R log R d log V. Okay, so in the special case where Cp is independent of temperature, I can take the Cp out of this integral. R is anyway a constant, so it can be taken out of this integral. So if Cp is constant, that is independent of temperature, this approximation can be done if the temperature range is very small, because Cp varies very gradually with temperature, in which case in small changes of temperature you can take this as constant. So then what we get is so delta S, which is Sf minus Si, is Cp log Tf by Ti plus, sorry, not Cp, it should have been Cv. Actually, I've been making a mistake of that everywhere. Yeah, this is Cv, so this should have been Cv, this should have been Cv, this should have been Cv, this should have been Cv. Okay, so let's come back and write that. Yeah, Cv, 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 and Cv. So this is Cv log Tf by Ti plus R log Vf by Ti. Okay, so this is one expression for calculating change in entropy. So this is one expression that we have. The next expression, okay, the next expression that we have for the same quantity ds is, if I start with Tds is equal to dH minus Vdp. So this is the other expression that we had seen in the earlier part. So if I divide throughout by T, I get ds is equal to Cp dt by T minus V by T dP, and since PV is equal to RT, V by T is R by P, so this is Cp dt by T minus R dP by P. And if I have the integral, so then I get SF minus SI is integral from Ti to Tf of Cp of T into dt by T minus R integral from Vi to Vf of dP by P. Okay, so this is your expression. So you can calculate this delta S either using this expression. So let's call this as equation number 4, and if we go back to the previous page, we call this as equation number 3. So you can calculate the delta S from either equation number 3 or equation number 4. Now similarly, internal energy changes can be calculated using these expressions. Basically we said dH is equal to Cp dt, so integration will give me delta H is equal to integral from Ti to Tf of Cp dt, and similarly delta U will be equal to integral from Ti to Tf of Cv dt. So what normally is done is at some value of temperature arbitrarily for any given substance, this H is chosen to be 0, and from there the delta H can be evaluated for every other point. And so if you have a T ref at which U at T ref is 0, then H at T ref is going to be equal to 0 plus RT, because H is equal to U plus PV, which is U plus RT. So this R into T ref. So that is your starting case, and using this as the origin or datum, we can evaluate the Cp and we can evaluate the H and U at any point using this delta H starting with Ti as T ref, and you get the value of H everywhere. And similarly, U and H are evaluated the same way. S is also arbitrarily defined as 0 at some temperature, some reference temperature, and then you can use these expressions. You can see that then the change in S alone is affected by the ratio of volumes in this case, or the ratio of pressures in this case. So if I, for example, take constant Cp, this becomes equal to Cp log T2 by T1 or Tf by Ti minus R log Pf by Pi. So this is an expression that we get for constant. So you see that the entropy change depends on pressure ratio or temperature ratio. So it depends on the pressure of the gas, whereas the internal energy and enthalpy changes depend only on temperature. So this is the thing that we see, and you have these things evaluated. So for ideal gases, you have tables of temperature versus U, H, and S naught, where S naught is actually S at T comma P ref, where P ref is an atmospheric pressure. Okay, so then you can actually calculate this using this S naught, and for pressure change it is corrected using this expression. So that is the thing that we use. So S2 minus S1, or SF minus SI if I want, to be equal to S naught at Tf minus S naught at Ti, which is actually equal to this quantity, and minus R log Pf by Pi. So this can be looked up from the ideal gas tables, and this can be evaluated for the pressure ratio. And for internal energy and enthalpy change, since this U and H are listed in the tables, you can directly evaluate them. You also have this U, H, and S, S naught, given as polynomial functions of T, or sometimes T by 1000, depending on whether it's expressed in joules or kilojoules. So then you can actually evaluate U, H, and S given the value of temperature. Instead of looking at the tables, you can use this. So if you have a computer program that needs to evaluate it, you can use these. And once this is available, because there is only a derivative, del U by del T will give me Cv, and del H by del T will give me Cp. So I can actually differentiate this polynomial expression with respect to temperature and obtain polynomial expressions for Cp and Cv as well. Right? So that is the way we actually calculate the changes in internal energy, enthalpy, and entropy for the case of ideal gases. Okay. So for this class, we'll stop at this point and continue in the next class for more complex forms of equations of state. We'll stop here. This lecture became a little longer than the usual ones, but I think that was necessary. Okay, we'll stop here.